morning, everybody. So we're going to present some of the results that we achieved in the FLUIDOS project, starting, of course, with what is the FLUIDOS project and why those results can be important also outside the project itself. So a brief outline of the agenda, overview of the FLUIDOS project, how to share resources, energy and carbon efficiency, security, use cases, collaboration opportunities, and questions. So given that we have a short time, we will ask you to make the questions at the end. So what's the original idea? The idea is that if you observe the current world, we have many existing silos. So why? There is no reason why, if I have my smartphone here, my application has to be executed exactly on the smartphone. Why cannot use the laptop that is nearby and so on? But if you look at the current situation, we have silos. Each device is a current silos, but even more surprising, this happens also in the cloud. So if you have a cloud computing service, maybe in Amazon, and you decide that maybe it's better to take GPUs resources from Google, you cannot, because if you are in Amazon, you cannot extend your cluster and take resources also in Google. And this is exactly what we would like to address in our problem. So the idea is to create an endless computing space where you have your devices, your cloud, and so on, that can take resources dynamically from any device, cloud, and so on that is nearby. So in the end, to create a sort of unique pool of resources where you can borrow and use and consume services and resources. So the end is to create a dynamic, endless computing space. So one more bit of information about our idea. So apparently, if you talk about the computing continuum, because this looks like computing continuum, is apparently here because we have already a lot of devices, cloud, edge servers, and so on. So what's the problem with the current computing continuum? The problem is the word transparency, because, you know, we have many silos and we can leverage them all, but when you deploy your service, you have to target explicitly, this runs on my laptop, this runs on my smartphone, this runs in the Google Cloud, and so on. So you have to decide where things are running. And with FLUIDOS, what we do is that the FLUIDOS, so this magic that we put in the middle of the computing, decides where things are going to be executed and where moved. So everything becomes transparent. So your application will be deployed in FLUIDOS, and FLUIDOS does the magic actually, and decides where each piece of the application has to go. FLUIDOS actually stands for Fluid Operating System, Fluid OS. That's the idea. So the FLUIDOS computing continuum defines multiple dynamic and secure virtual spaces spanning across multiple technological domains and administrative boundaries. So technological domains is cloud, edge, server, devices, and so on. And administrative boundaries means is mine, is yours, is for Google. So, you know, different owners that contribute to the pool of resources that we want to use. If you think about that, it's not that different from the internet. You have many networks sitting together, sharing resources, and we leverage them all in a completely transparent way. Okay? And this is exactly the key, transparency. So what's the stack? So what do we use in FLUIDOS in order to make this visual? Obviously, we don't want to reinvent the wheel, so we have a stack made by multiple components we reuse exactly what we have at the bottom, so devices, cloud, orchestrator, and so on. We reuse the server OS, so the operating system as it is. And then we have the first strong assumption, so that the world will be cloud native. So for us, an important component is Kubernetes. By the way, there are several components, several flavors actually of Kubernetes, so we can have a very powerful Kubernetes for the cloud, a reduced Kubernetes for the edge. So our architecture works also on Raspberry Pi on those things. And then we have Leco, which is an open source software that helps in creating the Continuum. And then we have FLUIDOS on the top, so our components there. So just to be a little bit more clear, what's the difference between Kubernetes, Leco, and FLUIDOS? So Kubernetes and Leco are providing, let's say, the workhorse. So they created the basic components in order to create the Continuum, but they are not able to orchestrate the Continuum. So here is where FLUIDOS comes in. So FLUIDOS introduces command and control intelligence, such as resource negotiation, orchestration, security, energy, and carbon efficiency on top of everything, so that the Continuum becomes intelligent. And FLUIDOS defines a platform, so it defines in the end a software, proof of concept software, to make the computer continuum transparent and real. So many challenges, of course, we have to solve. We just presented or listed them here. We cannot, of course, present everything here today, but we will have a few short on what we feel is particularly interesting here. The first is a protocol about available resources, negotiation, and so on that we presented immediately later. The second is the orchestration capability that we have, particularly in order to privilege green energy and carbon efficiency. And the third, quick shot on the security. If we want to leverage an infrastructure that is not mine, of course, security is very important. And finally, we would like to give a few words on the problem of assessing the FLUIDOS vision in use cases and possible collaboration opportunities through the open calls. And this is the end of the introduction. Thank you very much. The first component that we would like to present is the real protocol. So let's start with the problem. We say that we have a fluid system, a continuum set of resources. So we have devices, IoT devices, servers, cloud, and so on. But we have a fundamental problem if we want to leverage all those resources. So where are those resources? Which are their characteristics? What can you give me? A virtual machine, a CPU, a GPU, a service? What? So which are the characteristics of the resources I can leverage? Once you know that, can I reserve some of those resources? Of course, I cannot buy everything. I have to choose. I have to reserve. Can I be guaranteed that the resources I'm looking for or I would like to reserve will be actually reserved to me? Can I pay? So, okay, can I sign a contract? And then can I set up a physical infrastructure, actually a virtual infrastructure, in this case with Leco and Kubernetes, in order to actually leverage those resources? So in order to solve the above problems, we defined a new protocol, which is called REAR, that stands for Resource Advertisement and Reservation Protocol, that addresses 4 key objectives. First, has to be standard, because when you interact with different people, of course, has to be standard. Second, has to be extensible, because you don't know what other people are looking for. Maybe you are just looking for GPU, but somebody else may be looking for a sensor or for data or whatever resources are available out there. So there is a full world of sensors, information, and so on. We have to be absolutely open to any kind of information we can look for. Third, decentralization. We don't want to have somebody that becomes an owner of the system. Think, for example, the internet. That's a very nice example of decentralized system. There is no single owner there, and the same should happen for our negotiation, resource advertisement, and reservation protocol. And of course, security and trust. Security is a very important keyword here, given that the resources are not all under my control. So, how does it work, the RIA protocol? Basically, it's very simple in principle. I can ask somebody, which resources do you have? And then it returns back me the answer, and so on. There will be a slide later on that. But in general, it supports two kinds of interaction. What we call horizontal interactions, like the customer is asking to the provider, which resources can you give to me? And the provider returns, say, okay, I prefer this resource with those characteristics. Can I buy? Okay, that's a horizontal negotiation between the customer and the provider. The second model is what we call vertical interaction, so that the customer negotiates with an intermediate system that can be a broker, and then the broker negotiates or has already negotiated with the resource provider. So in principle, the broker may not have any resources to sell, but it can resell resources that are bought from another third-party provider. So it becomes more complex, the system, but it opens up new interesting use cases and business models as well. The protocol that we defined supports both interaction models here. And what do we advertise? What can we buy? Okay, we say that one of the keywords here is extensibility. Of course, we have to start from somewhere, and we decided 5 kinds of objects right now. So a Kubernetes cluster, that for us is very important given that FLUIDOS heavily is based on Kubernetes, but this protocol doesn't solve only FLUIDOS problem. It's more general. So we define also the capability to buy and acquire VMs, to buy and acquire applications, so like services. Just, I want to have a database as a service. Give me a database. Okay. And then sensors, I would like to have access to a GPS sensor, and then data. So, of course, this is not everything that we should have, but this is open, and then you can extend this as much as you want. The flow of the messages is, in principle, rather simple. I'm just showing here the messages without the security, because, of course, with the security built in that we have in the protocol, it becomes much more complex. But, okay, list flavor means show me the resources that you have, and this returns back with the list of resources. Then I can choose, I can decide to reserve what I need, and then I have a sort of okay from the provider. And I have also a field which is time to purchase. So you have to complete your purchase within, let's say, 30 seconds, so that, okay, the consumer can still think, okay, should I buy you or something else? 30 seconds to decide. Okay, and then when you decide, okay, you sign the contract and you get the okay. That's more or less the idea in the protocol. What we feel is that this has a huge range of applicability in the IoT edge continuum addressed by FLUIDOS, because we can use this to acquire resources in Kubernetes, but to acquire VMs, So there are applications in the telco market and so on. So we feel that this protocol is not really something that relates only to FLUIDOS. And this is why we have a very strong commitment on opening everything in terms of specification, code, the preliminary implementation, and also, of course, it's a research project, also a scientific paper. Conclusion, I think that I already said almost everything. I can take the chance to show you a brief view of the protocol here, actually with our implementation. So we have the remote cluster here that is able to see some remote nodes. So like you have two clusters, okay? So the remote nodes are not yet being contacted. So right now you have a given amount of resources, CPU and memory, and you would like to acquire something. By the way, the protocol is bidirectional, but you know, right now you have nothing available, so you didn't have acquired nothing. You have also some local resources here because the protocol is bidirectional, so you can also export and sell your own resources. Like, okay, I can define what I would like to sell myself, okay? This, like, I would like to sell this Tesla because I'm not using right now. But let's move to the acquiring resources, okay? In our implementation, this is called the solver request, okay? So this basically, we created this information in the protocol that triggers the generation of list resources. I can ask the other party to list everything, okay? Or I can decide to use filters. So say, I'm not interested in VMs. I'm interested only in Kubernetes cluster. Okay, fine. Show me only Kubernetes cluster. And by the way, I can also decide some characteristics. I do not care about the very small cluster. I need at least one CPU, at least 1 gigabyte of RAM. So please do not show me things that are smaller than those. So I can send a request, and this request is being sent on the other side. Okay, this is our dashboard that shows that everything has been completed successfully. And then you can get some new flavors on the available list. So those are all the resources that you can actually acquire. Okay, so this is actually this phase of the protocol. Now you have to decide which one you have to buy. Okay, so from the long list, you have to decide, okay, I think the first one is the one that is interesting to me. I can click buy, and then what we call allocation, a computing continuum between my cluster and the remote cluster is established, so that we can start exchanging data, computing, and all that stuff that I need to do. And this is the end of this presentation.
Hello, everyone. My name is Nasir, and I will briefly walk you through energy and carbon efficiency in FLUIDOS that Fulvio just presented. So let's start with energy efficiency. In traditional setups where tasks are handled either by cloud servers or local devices, these systems are not efficient. So devices often run at high power even for lighter tasks. In this figure, we can see a sample server CPU, and it is using over a quarter of its maximum power at active idle, which makes its performance to power ratio quite miserable at low utilization rates. An edge-to-cloud continuum would enable us to shift those lighter workloads away from capable but power-hungry cloud servers to edge devices, for example. So we don't need to power up those servers, and we can save the energy by shutting them down. And through such a fluid workload distribution model, we can save up to 25% of energy, according to our experiments. But what about carbon efficiency? So a sign of equality has stood between those two terms for quite a while, and this is true to some extent. Improving energy efficiency does passively improve carbon efficiency. However, the reality is that on the micro scale, we have Moore's law slowing down, and on the macro scale, the PUEs of hyperscale data centers are already reaching 1. So higher and higher capital expenditures are resulting in diminishing returns on carbon efficiency. So we must tackle carbon efficiency directly and additionally to energy efficiency. And this is a very sore topic for us environmental scientists, and it all comes down to reporting practices. So one approach is the so-called renewable energy match. A balance for a company's energy demand is drawn at the end of the year, and carbon neutrality officially can be claimed if enough renewable energy has been procured over the course of this year. Being a market-based approach, it is prone to accounting manipulation, so to speak. So this approach, what I'm trying to say is that the benefits of this approach are questionable, and they are being questioned. And coincidentally, just 10 days ago, The Guardian has published this article highlighting again the discrepancy between the reality and the numbers on paper for the big tech. So the way to do this is actually having 24/7 carbon-free energy. We balance our renewables per hour, per each hour of the year, and per location. And only this way we can claim true carbon neutrality. And for that, we need to shape our demand. One of the greatest new developments in the field have been platforms providing data, both live and forecasted, for carbon intensities, such as this from electricity maps. These insights allow us to shift our workloads across locations and in time to benefit from greener energy. In this snapshot of production in the European grid, taken at around 2 p.m. on a sunny day, dispatching workloads in France is at least 5 times more carbon efficient than in Spain, and at least 10 times more carbon efficient than in Germany. So we can benefit from this quite big differences in carbon intensity. But electric energy that we've been talking about so far is not the only contributor to the carbon footprint. So let's take a brief look at the life cycle of our hardware. It all starts with the manufacturing phase, then transportation and distribution to the end users, the use phase where we consume most of our electric energy, and finally recycling. For carbon, transportation and recycling are negligible, so we only focus on use phase and manufacturing phase. And the use phase, or the operational emissions, they have been addressed in the previous slides about electric energy, but the manufacturing phase, or the embodied emissions, are still missing from the picture. So to consider those two types of emissions in conjunction, we need to introduce a new metric, such as total carbon footprint. And to bring those two types of emissions to common denominator, we need additional metrics, such as the power consumption of the workload, the lifetime of the hardware, and finally, the execution time of the workload. These total carbon footprint values can then be visualized in a grid like this, where we have locations or our available nodes as rows and time slots as columns. After this grid is compiled, an algorithm is selecting the green a cell, and the workload is dispatched accordingly. Finally, it's safe to say that no one will really look into optimizing carbon efficiency deeply without securing the energy costs. And we do have to pay with energy overhead for the privilege of being flexible in our execution. However, the benefits stand out when we consider both efficiencies jointly. So for example, a policy that is doing temporal shifting for a sacrifice of just 5% of energy can boost our carbon efficiency by up to 30%. Thank you.
So, hello everyone, I'm Luis, I'm from Fundación Bruno Kedler, and I will talk a little bit of security, or more specifically, the enforced security on the edge cloud continuum. But before talking about security, because security is a generic term, we needed to understand the objectives inside of the project and the objectives of security in our user case. So the first thing that we want to ensure with security is ensure that the FLUIDOS node is what it claims to be, is the one that claims to be, and also we restrict it access to the resources that we already negotiate and we already defined. After, we want to offer an environment where the user or cloud can run untampered, that means without any alteration, and provide evidences about its integrity and the compliance in infrastructure. So we needed to ensure that it runs in the correct way, but we also needed to prove that it runs in the correct way. After, we want to defend the users from intrusive providers and also the providers from malicious users. Because we want that since we are using resources that it's not owned by us, we needed to ensure the security on that. And finally, we needed to manage security in an automated way and avoid affecting workload performance. So in the end, the two main objectives, we can resume all of that in two main points: that ensure that the application from the user is secure and ensure that the infrastructure from the provider is also secure. And how we can do that? How we can enable the security in the infrastructure? It's not a simple thing, because we needed to attack several different aspects of the security, and to that we needed to implement a lot of software or methodologies. So we needed to implement new solutions in authentication and authorization, in workload confidentiality, and so on, like cybersecurity, cyber deception. But based on the constraint time that we have here, we will focus in a single example, that is attack that we discover in this kind of topology and in threat detection. But to talk about the attack, first we needed to recall a little bit how it works, the infrastructure of FLUIDOS in the background. So of course we have the Fluid Continuum interface, but in the end we have a node or a cloud from the consumer, a cloud of the provider, a cloud node from each one, and each one can start applications in this specific infrastructure. So I have my own Kubernetes node and my own Kubernetes cluster, and I can deploy my apps there, and then the provider will have its own Kubernetes nodes, and we will deploy the applications there. And at some point, I decided to negotiate, and I create a request of for resources in the provided by the consumer. So in the infrastructure view, what this will create a space in the provider cluster where I can put these resources. So I can put my applications there, but I cannot forget that this is just a space inside of the provider infrastructure, and I can still deploy applications there if I'm the provider, and I, as a consumer, can deploy the applications in my own cloud. But more specifically about the provider node, when we have the node, we have the applications from the provider, and then we decided to get some amount of resources in that specific node. So we will create this consumer resource space. And what is the idea of the security? The idea of security is ensure that this border between the resources that the FLUIDOS will enable to a specific consumer will be completely separate from the applications in the infrastructure from the provider or for other consumers. So when I start an application inside of this space, I want to ensure that this application is completely isolated from the infrastructure, and the infrastructure will not suffer with this application because the application are using more resources, for example, than the one associated to them. However, we needed to recall that not always I can do that, because I have the control plane, I have the part of the control plane that I can manage the network connections, I can manage the quotas and resources that I want to give it to a simple application. But some parts of the topology I needed to share. And one example of that is the container runtime. And the container runtime, one of the bigger problems on that is when I started to instantiate applications in the infrastructure, he will not understand that I'm instantiating an application in the isolated environment. So if I try to create several applications at the same time, it will work as a single node. And since it works as a single node, one of the limitations of the container runtime is he has like a queue of applications that I needed to instantiate. So I needed to follow this order. So if I have a space and this space started to instantiate applications, during the time where these applications are instantiated, I will block the node to the other consumers or even the provider. And how we can use that to create an attack? So sorry for the typo, the bottom part is control plane, not the data plane. So when I try to create an application, I will create an application in the control plane, and FLUIDOS or Kubernetes will receive this request and will send this request to the container infrastructure. And this application will be starting in container infrastructure. So in the perfect world, when I send a delete, this information will be sent to the FLUIDOS, and the FLUIDOS will send this information to the container infrastructure, and I will delete the application. But if I decided to create an attack that is basically overusage of the network, creating and deletion requests at the same time, what will happen with the infrastructure? I will create the requests to the FLUIDOS, the Kubernetes. They will send it to the container infrastructure, but at some point, I will overload the system, and I will start creating a queue. What's the problem with that? The problem with that is that, and this is a problem in the container infrastructure, when I create these new applications, and this application is still in the queue, when I delete it from the FLUIDOS or the Kubernetes, it will not delete it from the queue in the container infrastructure. It will maintain it there until it finishes that phase, and after it's ready, it will execute the next command that is the deletion. So what this means is, even if I send a delete request and it is completely deleted from Kubernetes, it is still in the container infrastructure. And since it is still in the container infrastructure, what happens is, if I have too many applications, my container infrastructure will be unavailable. So how can we solve this problem? So since it's a problem in the container infrastructure, and it's something that we cannot manage per se, we needed to intercept that. So we developed a solution that is called Magic System. That is, the idea is, every connection that we made, every request that we made to FLUIDOS, we create also a copy of that inside of the Magic System, storing the information from the request. And we will store that until the download and the instantiation phase is complete. So we do that through the TCP connections and the syscalls in the container runtime, and we check it and we save it during this time. So when someone sends a lot of requests of creation and deletion, we will store these creations in our database and check the connections in the container runtime syscalls. And when we receive the deletes, that is deleting the FLUIDOS or Kubernetes, what we will do is check it in our database and sanitize the queue, so the container infrastructure will have the same behavior as the control plane is showing. It's important to notice that is not just a problem with FLUIDOS, but that could happen in any case that we share infrastructure, because since we share infrastructure, a lot of users can send requests to the same infrastructure. So I will show a small demo. I think that the video is okay, but it's a little bit of black screen because we are talking about security. So maybe we'll jump some parts. Okay, so first here we are showing that we are pitting the resources between a provider and a consumer. Here we are creating a namespace inside of the cluster, and we are sharing it through LiPo to the consumer. So here is just proving that the namespace is creating. So we have the rising consumer in the provider, and then we have the consumer context in the model one. And now we are instantiate a container, just instantiate it inside of the provider's node. So we create the pod, and here we are showing that the pod is already created. So we are creating it, and we check where it was deployed and was really deployed in the provider. So here we can check that the correct cluster is the provider one. And if we check there, the pod is creating because we needed to download the image, so it took some time. And we can check in the resources in the provider that it is using a lot of CPU to download this image, because in this specific case, the images are a little bit bigger, so it needed to download, decompress, and so on, so it will use the processing time. But the point is, even if we delete the request from the pod deployment, it will not delete when it's in downloaded image and instantiated the application. So it will pending until, just a little bit, that I was explaining and was too fast. It will not delete until it's still downloading the image. So he needed to finish the image download to stop and delete the container. So here we are using the same example, but now running our solution, the Mage system. And when we create the application and we run the pod, it will receive here an image request. So we know that we are downloading an image. So when we send the delete, it will know that it needed to delete the image and will delete the request. So instead of waiting, the completed download to delete it from the request, they will download it, stop it automatically. And the main benefit of that, we can check in the resources. So instead of that I continues downloading the image that here it is started, it delete automatically. So the resource usage is basically negligible. And if we check in the topology, the resource is not there anymore. So, as conclusions, that is just an example. And an important thing is the security is an intrinsic part of the FLUIDOS project. And Magic is only one of the several projects and tools developed by FLUIDOS. By the way, Magic is also open source, and basically all the projects inside of the Kubernetes, inside of the FLUIDOS is open source. You can check in the website from the deliverable 5.1 that presents a more complete definition of the security framework. And also you can check other security papers that can be found in the website. And thank you. And I also finish.
Thanks a lot. So we'll jump on. So this is the topic. So you've seen various pieces of very interesting technology today, and all from the technical perspective. The question more so now is how is FLUIDOS actually being used, let's say, in the real world? In FLUIDOS, we have many, many interesting uses of that. How do I know? I know because whatever about my actual internal project responsibilities, I'm an actual user of FLUIDOS myself. I work for a company, TerraView. TerraView, we create vineyard management software. So we call it a DSS, a decision support system. And that's a big system that takes from many sources of data, from IoT sensors, from satellite imagery to drone. And we bring it all in and we then process it and present the understanding of how a particular crop, wine in our case, is doing for the producers themselves. It's all centralized, and so we find ourselves with this problem here, which is the problem of the current day, if we want to call it compute continuum. The compute continuum is, well, originally, and that this is the legacy of what we have at TerraView, is the cloud. The cloud provides us with all our resources, and that's where all our development operates upon. However, as we have progressed over time, more and more new interesting offers become available to us. So we have from the IoT, which is not shown here, but we have the far edge and back into the telco edge. And we would like to be able to take avail of these resources because most likely they're of cheaper, more cost-effective nature. But most importantly, especially from our perspective, they're closer to the end user. So if we can avoid having to pull data back in to the core cloud, all the better. Now, we currently have an application that is not just 6 components, it's actually 60 components. It's 10 times that. And our problem had been, before we came in contact with FLUIDOS, we had no way of actually managing this efficiently and effectively. Our team is relatively small in engineering. We've got about 6 people there. And to be able to manage multiple offerings from different providers was very, very difficult. In fact, it was impossible because of constraints. Moving on, we came across on FLUIDOS, and we got involved in the FLUIDOS consortium. And there, as Fulvio has already explained, the advantages of FLUIDOS was for us to be able to rely upon the FLUIDOS software platform, and to be able then to address and access the resources that were currently available in the now compute continuum. Very important for us was that we had minimal changes needed to be made in our application. Our application is described by a simple Kubernetes. Well, it's not simple, but it's large application stack. It's all as Helm. And we've had little modifications to be made other than to be able to say where the particular software components need to be placed. And that's important because we do indeed have these new availability of resources to us. And so it was here with the meta orchestrator that it's carried out inside of FLUIDOS that allowed us to provide intents, so the hints to where these particular pieces of computation need to happen. Now, if I go get in closer, the thing that we found inside of FLUIDOS, it solved the problem of it there being a continuum there of untapped resources. So FLUIDOS to us was able to offer us a simplified and a unified means to deploy and also describe and orchestrate our application. The intents were very important, as I said already, and so that was our intent-based orchestration work. And then we do have very different offers from different providers, and to understand which resource needs to be used best, the work that Fulvio also presented on the REAR protocol for resource recruitment and agreement on contract, that was very helpful as well for us. Furthermore, it's not just a static deployment of the application, but once the application is up and running, there's an element of dynamic distribution of the workload, such that the workload can be moved backwards and forwards where it makes sense. And very important to us was the seamless communication. So many of us perhaps have used Docker in the past. Accessing Docker and accessing the applications on Docker was very easy because you essentially had a transparent network, but that was only on your developer laptop. If we moved forward, and I spent a lot of time working in OpenStack, so all the way back in the Bexar and the Cactus releases, they had a lovely flat networking set up there that you could easily access your virtual machines. But that was still constrained to the data center. What we have now with seamless communication that Liquo and FLUIDOS brings to us is not just access within the data center, but right across the full cloud computing continuum itself. We talked already today from Nasir and Luis about the various additional features that are available to anybody using FLUIDOS, and they're the security features and the energy optimizations. And they're elements that we would love to be able to access and will access and use within our experimentation. So exercising the platform, we originally started with 3 use cases. There was a use case from RSE, then robotic, and then TerraView ourselves. From RSE's perspective, what was needed there was to be able to take avail of FLUIDOS and apply it into a highly complex system of power distribution. You have power distribution that starts at the actual source power plants. That's the high voltage network that comes down into the distribution networks, which is medium voltage, all the way down to home, and that's the low voltage. Right throughout that complete network or networks, you need to monitor and you need to account for all the power that's happening there. That's very important that that system never goes down and it's always reliable. And it's FLUIDOS that's providing the means to be able to do that. And currently that's their under work and prototyping. For Robotnik, what was very important for them, they run a use case on robotic logistics. And there, it's very important that the robots run and work as often and as long as they can. The optimizations that FLUIDOS brings to this particular use case is that we can offload particular workloads that are not necessary for the operation of the robot at the time, move them off to an edge node where they're still connected and the work can still continue. And ultimately, the big gain here for Robotnik is that the robots work for longer. And then finally, ourselves in TerraView, what was very important for us was to be able to do the processing of data locally on the edge, on where the production is happening. So essentially in the farmers' vineyards. And there what happens is that a lot of data comes in, be it from sensors or typically from drone surveys. Drone surveys these days can go to 200 gigabytes. No surprise, vineyard operations are out in the countryside. Countrysides don't necessarily have the greatest amount of bandwidth. So to even put 200 gigabytes up over a connection into the central cloud, that was time consuming and difficult and at times impossible. So what we've been able to do is move that image processing and put it out on the edge for the agricultural indices to be extracted and for that small bit of information then to be given to us in the core. I said that there's 3 here on the slide, there's 8. In the last open call, we had an additional 5 use cases brought in. It's all largely a mix of SMEs, and we have one of the universities there. So if I just quickly do a quick overview of these particular use cases, we have Diacle from the University of Patras. This is to do with power line inspection by drones. They're doing hierarchical inferencing. So the idea there is that to look at the particular problems in the only do small amounts of processing on the drone themselves. I'm a registered drone pilot. I understand how important it is to maintain battery. So the idea here is to do a small amount of processing on the drone and then bring it back up through the hierarchy where further inferencing can be done. They're leveraging the orchestration and adaptive workload placement features from FLUIDOS. On to the second is DIAS. That's from Smartly. This is a distributed edge analytics that takes avail of all the resources that are there from small cells, small devices in 5G networks to allow for the analytics to happen. And there we've got from FLUIDOS supporting dynamic workload distribution and resource recruitment. We have Fusion Check. Fusion Check, there's many devices scattered right across the cloud computing continuum for IoT, edge, and cloud. And there we need to be able to manage all of these in education and health environments and also manage those in a usable way through a dashboard itself. We have Target, the second last. Target is all about data space, and this is somewhat similar to what we do in TerraView, where we move the computation closer to where the data is. In data spaces, there are large data sets, much greater than 200 gigs that we would have. They're in the terabytes, petabytes. And so the idea there is to bring, indeed, the computation to the data. And here we're leveraging the FLUIDOS capabilities, dynamic workload distribution, and naturally bringing the computation to the data. And finally, then there's FLUIDOS. That's, at the moment, it's a siloed home automation stack. That's very much like the same situation that we have in TerraView. It was siloed and is now being made ready for the cloud continuum. They're using the unified and simple intent-based deployment. We're not done yet. These use cases continue, but we're also inviting for more. There's more coming up in open call. I won't say anything more. I'll leave it over then to James. And for the time being, I'd like to thank you for your attention. Thanks a lot.
Good afternoon, everybody. Thank you very much, Andy. So my name is James Philpott. I am a project manager at Digital SME, and we are in charge of the open call in FLUIDOS. So good news, as Andy mentioned, we have money and we would like to give it away. So we have 120,000 euros that we will award to 5 different grants. And for those of you that aren't aware, I'll just explain. These are known by different names: cascade funding, financial support to third parties, or sub-grants. And these are something particular to EC projects. They're not subcontracting, so they are awarded through an open call where we request project applications. We select the ones that we think best align with the FLUIDOS goals, and then we award the grant so that the applicants can implement their project idea. So as Andy mentioned, we have one currently running, which was funded back in June, and there is an application period open for another round of applications, specifically focusing on use cases. So these are available, the grants are available for both individual applicants and small consortia. So as you saw, up to 3 entities can be part of a consortia, and the grant amount is 120,000 euros, no matter the size of the consortium or the individual applicant. And the grant is awarded with an application, with an obligation rather, to undertake the specific work that was sent out in the application, with reporting back to the project on the progress and the results obtained. Okay. So some practical details about the open call. The deadline is the 4th of October, so that is next Friday. So there is only a short amount of time left, but the application is not onerous. It is completely possible to write a good application in the next week and submit it. What we need for an application is, of course, to fill an application form. So there's details how you would use FLUIDOS, the benefits it would deliver to your company, so the impact of FLUIDOS, and then how you intend to work on the project. So the information on kind of the resources you would put towards it, and how you would kind of measure the progress of the sub project itself. And then we just need this declaration of honor, which is that you agree to do the work that you've set out in your application. And if you are an SME, we just need to make sure that that's the case, so you conform with the EU definition of an SME. Alongside this, to help you with your applications, we offer the FLUIDOS Champion Service. And so these are project partners that are available to discuss your proposal with you and help make sure that you align more closely with the FLUIDOS goals. So as I said, we are looking for use cases. So the idea is to take FLUIDOS and deploy it in your particular area and measure how well it performs, see if it improves your service. If not, that's also a valid outcome, because we need to know this to improve FLUIDOS as it runs. So to apply, you go to our website. We can put the link later. And then you can send your application, and a partner will check that and then get back to you with some advice. So to give you some advice on applying, we have a lot of documentation online in the form of publications and deliverables. These are all available on the Open Call platform, and we really recommend you read these before submitting your application, certainly, but also requesting a champion, because it helps you understand the technology and also the goals of the FLUIDOS system. On the website, there are the guidelines for applicants. These detail the evaluation criteria. So this helps you write an application because you understand what you will be assessed on. So using these to construct your answer will help you write an application that is not only relevant to what we're asking, but also really helps you structure the application and why FLUIDOS will help you. Because this is the crucial point, is we are awarding this money to help demonstrate the validity of FLUIDOS. We want to see how well it runs. So you need to demonstrate the value of FLUIDOS to your system. How does it help you? What's the current state of the art and the way you do things? And what will FLUIDOS let you do better or differently? And this is the value we are looking to get out of it. And so that will help distinguish your application from others. So in this vein, it's really worth checking out the current use cases and the pilots. We are going to try and avoid duplicating something that's already done. And when we say something that's already done, it's not the top level name, say, of viticulture in TerraView's example. It's what are they doing with FLUIDOS? So if you work in manufacturing, but your application will do something similar to another one in a different domain, that is still a duplication, and this will be part of the assessment. So it's worth making sure that you avoid overlaps with currently existing use cases. And finally, if you are integrating FLUIDOS with your own software, it's really, really important to make sure you explain what your software does. The evaluators won't be looking beyond the application form, so they can't go out and look at your website and understand what your software does. You have to explain it within the context of the application so they understand. And finally, if you have any other questions, we do have a dedicated email address for this, and we're very responsive. So we will get back to you as soon as possible to help you. And of course, there are other champions available as well. So I will finish now so we can go and enjoy sandwiches. But if there are any questions, of course, I'm happy to stay here and answer some. So thank you very much, and good afternoon.